Students, welcome to the class 3. So today we'll discuss regarding the nature of bandwidth intensity. Okay, so yesterday's class we have learned regarding the different microstates, how we can calculate the microstates. So today we are going to learn the next concept, that is nature of the bandwidth width intensity. It can be asked for 2 marks, short question. So there are few reasons why there will be broad width in the intensity. So whenever we get this spectra, so always we get a very broad spectra like this, but in NMR and all we have seen that the spectra will be like this sharp peak will be there, but in UV visible we can see there is a broad spectra we are going to obtain. In Why? So this is because of the reason I have given here. So it may be because of natural broadening, or it may be vibrational, because of vibrational mode of transitions or spin orbit coupling, John Taylor distortion. Okay, then thermal Doppler effect and pressure producing effect. So maybe that. So these are some of the reasons why the spectra will be seen broad in the UV visible region here. So one by one, if we study the vibrational, so we can know that, see here, if you see take graph of potential energy versus interelectronic distance here. So electronic state 1 and the excited state here E2 E1. So this is a ground state here, and the electrons may be excited from nu 0. So these are different vibrational modes here. So nu 0 to nu 1, it may be nu 0 to nu 2, nu 0 to nu 3, like this. And the main concept here is the energy level between this vibronic, this is very less, so very less. Okay, that is the reason why the spectroscopic meter, so it fails to recognize or resolve these transitions. So it is not exactly from nu 0 to nu 0 to nu 0 or nu 0 to nu 1 here. So it may be nu 1 nu 2, like that. So energy is so less that to for the spectrometer, so it fails to resolve that such a very minute transitions, and that's why we get broad spectrum here. So I have shown here that relative intensity versus wave number. If you see here, so nu 0 to nu, so it may have the little less intensity, nu 0 to nu 1, then nu 0 to nu 2, nu 3, nu 4. So maximum absorption you can see here is due to nu 0 to nu 2. So from nu 0 to nu 2, like this, maximum absorption. But the spectrometer will fail to resolve these transitions too, because of very less energy gap between these vibronic states. And that's why with the result, what the result of this is, we get a broadening like this. So you see here, so we have got the broadening of the spectra here instead of the sharp spectra. So this is one reason why the bandwidth and the intensity varies here, because of the vibronic effect. Similarly, excitation to ground state, so it fails. That's why it fails to resolve, and this system is being explained by the principle of Frank Condon principle. Okay, so this broadening of the spectra is because of this Frank Condon principle, as I have explained here. Then the third one, we can see here, spin orbit coupling. Very sure we have learnt in the last class that yes, definitely spin orbit coupling is also one reason why the spectra is seem to be broadened here. Why broadened here? Because you know that because of the spin orbit coupling, what will happen? So we get different J values here. Yesterday we have done it while putting into the finding this of each configuration. We have seen that 3 4 J values we will get it here, and very less energy difference will be there. And because of the spin orbit coupling with different J values, the even the resolution of this peaks fails here. That is the reason here. So this is the reason also why we get a broad range here, due to spectrophotometer failing of the resolution is lost here. No, so that is the second result. And next is the thermal Doppler effect. So Doppler effect mainly when the substance we take in the gaseous form. So we can see that the thermal Doppler effect also plays into important role for this broadening of the spectra. So as the temperature is increased, the Doppler effect means is what? So you stand at one place, and when a vehicle is coming from far place, so you hear the noise very less, and as it comes to you, you hear the noise very loudly, and as it goes away from you again, the noise is been lessened here. So this is what the Doppler effect. So whenever you are making the substance in a gaseous form, so the detector will be there. As the gases move towards the detector from far side, So initially there will be less velocity, but as it comes to the observer here, so detector, it will be more velocity. Again it goes from the detector far away, again the velocity decreases. So with the help of this temperature difference as well as the velocity of the gas, so we can see that the broadening of this peak will be obtained here. So natural broadening is there. So this is what the Doppler effect in physics. They are learning in more of this Doppler effect. So only in the examination point of this, you can see that vibrational mode and this spin orbit coupling is very much important. Yes, Doppler effect also you can write. You can mention. Then there will be natural broadening. So that is because of the electron excited state. So when it excites, it depends on the decay time, how much it is remained on the excited state in the excited state. So that is also one reason of the natural broadening, that why the spectra is seen to be broadened. The next is because of the pressure. The pressure role, as we have learned here in the as we have seen here. So one of the reason for the broadening is pressure producing, or pressure. So this is how it happens, because of the role of the impurities, so if impurities is present, so it will affect the emission. It will affect the emission of the electron. So whenever it get excited, when it comes down, if impurities is present, then definitely it will affect the emission will be broadened. So it is not going to be get in a sharpened way. For example, if you see here, so if a polar solvent is being used, whenever you go for UV and you use a polar solvent, definitely there will be the due to the hydrogen bonding will be there. So because of the hydrogen bonding, you can see that the spectra will be broadened. So there will be interaction, and the spectra will not be in a sharpened way. So this is the reason why we get broadened spectra as well as the intensity variation. Now if you see here, one typical spectra I have given with respect to absorption versus wave number. So this is a normal spectra, absorption spectra we have got in broadened way. Now you can see here there are two types. So in second case I have shown here this way, where the lambda max now is been increased, and in one case it may the lambda max is shifting here. So this we observe whenever we go for the different species. This is one species, and whenever we add another B component to this species, so either we can see this mode of absorption, or we can observe this mode of absorption due to all these factors. Then how you name this, how you come to know what is happening here. So whenever the absorption is going in the longer wavelength here, so we call it the bathyschromic. So bathyschromic red shift we call it as a high wavelength. The shift of the spectra will be for the high wavelength, that is the interaction, and the shift of the spectra will be for the higher wavelength. In some cases the interaction will be such a way that the absorption will be on the lower side. So this side you are going to see here, see this is absorption lowering. So lowering, why that we call it as a blue shift. So your red shift for higher wavelength shift. So lower wavelength shift we call as a blue shift. So hypsochromic. So that word is the technical word we call as a hypsochrome. So hypsochrome and bathochrome. So these are very important technical words we use in the absorption spectra whenever there is a shift in the lambda max values due to the interactions, or due to the species or impurities. So this is how, and this is a lowering of the intensity, and this mid place what we call it as a hypochromic intensity. So this is what and the intensity decreased, the intensity will be decreased. This is how, so we can explain, this is how we can show for the nature of the bandwidth intensity. So for 2 marks or 3 marks question, so this is how you have to explain with these diagrams. Okay, wherever requirement is there, you can show the diagrams. So you can show this also, and for research purpose, you can I have told you this important technical words which is used for during the absorption spectra. And this is how the one part of your chapter unit 1 is completed here. The next part of the unit 1 is very important. It is Orgel. I think you have learned this in previous semester regarding Orgel. What is this Orgel diagram? Orgel, and this time you are having a new, that is TS diagram. TS diagram, Tanabe-Sugano diagram. This is you are going to learn in the next concepts. Okay. So what is this Orgel diagram? So few points we will learn today, and next class we will see that we will learn little bit of the Orgel basic, because already I have learned in the previous semester here. So very fewly we will touch it, and this will not be asked too much also for this your third semester. Then we will divert directly to the TS diagram, which is very important, and where there is calculation part here. And what is this Orgel diagram? Orgel diagram, so you know that here the transition is considered only of the same spin multiplicity. So from example yesterday I showed you triplet A2G to triplet T2G like this. So wherever there is same spin multiplicity, so you can see such type, so you can see the Orgel diagram. Whenever the spin multiplicity is different, so here it will not work. So there is a TS diagram you have to work, you have to learn in this semester. Second thing is what the main disadvantage I can say, that it is only for the weak field ligand or high spin. So only weak field. So strong field ligand, low spin is not considered in Orgel diagram. So this is the second drawback. But it is very good for only weak field ligand. So that's why again the limitations. So you are going to learn the improvement in the Tanabe-Sugano diagram, TS diagram. And third point of this Orgel is it is a qualitative. Qualitative means it doesn't have any problem solving. So you are not going to solve any of the problems with respect to Orgel diagram. Okay, so it's a qualitative basis, qualitative, not a quantitative. So this is the third thing of this Orgel diagram, and it's a correlation diagram which determines the energy of a term of highest spin multiplicity. So Orgel diagram is a correlation diagram. So it is a core. We will learn this in the next slide. What does this mean? Correlation diagram which determines the energy of the term of highest spin multiplicity. So these 3 points or 4 points you have to keep, remember this for the Orgel diagram. So which is contradictory with the TS diagram. So they will ask difference between Orgel diagram or advantage of TS over Orgel. So these 4 things you have to keep in the mind. In the next class we will learn regarding the Orgel diagram flow chart as well as comparison with the Tanabe-Sugano diagram. Hopefully, so make points all of you, write down nicely. If again I am telling you, if you have any doubt in this, anytime you can ask me, interact with me, and come for the solution purpose. Thank you.